Hey, Mr. Simon here. We're going to go through algorithms and abstractions. We're getting ready for the create task, which is going to ask us a couple questions about those. So an algorithm is just a step-by-step process, and it can have as few as 2 steps. Here's a very simple algorithm. We're going to make a smiley face. Step 1 of the algorithm is to draw the head, and step 2 is to draw the face. It is a 2-step process because the order is important. You don't want to draw the face first. Then you would draw the head on top of it and cover it up. So it's a step-by-step process that accomplishes some task or job. Now, when you break that down, you'll notice that actually drawing the head is a algorithm in and of itself. To draw the head, we need to change the fill to yellow and then draw an ellipse. That's a 2-step process. To draw the face, we need to draw an arc for the smile, set the fill to black, and then draw 2 ellipses for the eyes. That's a 3-step process. So we have a 2-step algorithm that has sub-algorithms. Each of those steps actually has an algorithm inside of it that we need to perform that particular step. Here's an algorithm for a Tron game. So in our draw function, we're going to check to see if the game is over, and if not, we'll let the human take a turn, and then the computer will take a turn. And we're just going to repeat this process because the draw function repeats over and over until the game is over. Again, these are fairly simple ideas, right? Human takes a turn, computer takes a turn. There's a lot of code in when the human goes to take a turn. So there's a big sub-algorithm here. So the human function checks to see if the human crashed, draws a point wherever the human is currently located, and then it checks to see if the autopilot is on. If it is, we call the self-drive function to avoid obstacles. And then we go in whatever our current direction of travel is. Same with the computer. Check to see if the computer has crashed. If not, we draw a point at the current location of the computer. And then we call the comp drive function, which is a lot like self-drive, but the computer doesn't use an if statement because it always needs that to determine whether we're going to crash into something. And once that's completed, then we move the computer in the correct direction. On the create task, it's required that you have an algorithm that has at least 2 sub-algorithms. And you can see with my smiley face function, you don't need a complicated program to accomplish that. Now, your algorithm should have math or logic. Any sort of arithmetic like adding or subtracting, which I did in my smiley face, counts as math. Random numbers count as math. It's easy to meet that requirement. In my Tron game, I actually used logic. Logic is making decisions, so I use if statements to decide whether or not I'm going to crash into something and adjust my direction based on that. You don't need both. Somewhere in one of your algorithms, you need some math or some logic. And that's it. Okay, once you've got it, you're good on the algorithm requirement. So let's go to abstractions. Abstractions are simplifications. A good rule of thumb is when you use a single word like computer to represent something complex, like the turn a computer would take in a Tron game. There are a lot of abstractions in computer science. Functions are a great example where we use a single word like computer to represent a more complicated process like controlling a computer player in a Tron game. But there's others, lists, arrays, variables, and classes. Most of those are going to be outside the scope of this course, so we're going to concentrate on functions as abstractions. Now, a requirement for the create task is you must have an abstraction that manages complexity. Well, that just means simplifying things, right? Here in the smiley face program, I used a smiley face function to simplify and hide the details of the math that makes the smiley face. And this makes it easy to reuse, right? Instead of copying and pasting a bunch of ugly code with a bunch of math and trying to change it to make it work, I can just call the smiley face a second time with a different set of numbers. Now I'm going to have a different smiley face in a different position. So this manages complexity by hiding the details of the math and making it easier to reuse my function. It makes it easier to make as many smiley faces as I wanted rather than having to duplicate code that gets ugly and mathematical. In my Tron game, The human and computer functions both hide a significant amount of complexity involving the logic of whether or not the computer or the human is going to have a collision and changing the direction to avoid that collision. It makes the code more organized. It makes it easier to understand. It also makes it easier to modify once I have broken the program down into parts and arranged it. So all the computer code that controls the decision making that the computer makes on whether to turn is in the comp drive function. So I know if I want to make the decisions more sophisticated about how to make the Tron player avoid collisions, well, then I would just go to that function and concentrate there. I don't have to scan through the whole program for all different parts that might affect that. Hope this helps. Thank you for watching.